today's topic on the embedded electronics digital signal processing is about responses. So we are talking about if we have a box, any box, and put something in, basically what is the output. So basically that's our topic for today. And most importantly, actually there are few responses. A couple of those are in time space. So first one is the impulse response that actually will produce a, impulse. In means it gives you the impulse response out. Impulse response is usually marked as H of n. Okay, on the first exercise, some students actually mixed the impulse and step for some reason. But anyways, don't do the same mistake twice. Do it 3 times, then you learn. Okay, so, but then the unit step response is the other one. On the digital domain, the impulse response tells you already everything. But on the analog domain, that's the step response you can actually generate. So that's the Heaviside function, which is also used to test the analog systems, and that will give you something. Basically, you can test a system on analog domain, meaning in real life, taking a function generator output to any system and measure step response. Okay. But on digital domain, the impulse response is more useful, and there's also a nice feature that if you basically just make the first order differentiator, meaning the subtract the previous value from the next, the current value of the step response, you get also the impulse response. Okay, so that's basically the time domain stuff. So after that, if the system is linear, then you basically can feed it with any x of n, and you will get the y of n out. All right, good. So then on the frequency domain, we also have a couple of responses. Most important one is actually the frequency response. And actually the frequency response means, how should I actually do this? The frequency response actually is the same as you evaluate the transfer function on unit circle. That's the frequency response, which actually can be divided in 2 parts. First one is the amplitude response, which is just the absolute value of this one. And then you have the phase response as the phase shift value of that frequency response. That part is the phase response. Okay, good. So if you take a look at the zeros and poles of the system, then you can actually also make another form of the amplitude response. Let me mark it down here. It doesn't probably show up, but anyways. So the amplitude response part, EJ omega, and then think of the product form of the transfer function. You have the product from K0, 1 to N, also on the downstairs. Here we have the Z minus ZK, meaning Z minus the 0 positions, and here we have E to J omega, minus ZK. And this actually is a distance of a point in unit circle and the 0 location. And then that one is divided with the distances to pole locations, and that does product. Okay. So fundamentally, take a picture of that, and then we'll continue. Oh, that flash really helped a lot. Not. That one here. Okay, on 0 pole plot. If we have zeros, for example, on that kind of locations, and then few poles here, and then we have this E to J omega somewhere in here. That's the location on unit circle, where this angle here is the omega, which is simply 2 pi times the current frequency divided by sampling rate. Okay, so this is linearly proportional to the physical frequency, and then we basically have those distances. For example, distance to 0, 1 is here. And similarly, here we have the distance to pole 1. And if you start to look at it, so ratio of this distance to that one is quite high. So at this angle, our current omega, or somewhere here, and let's put here, for example, 1. This distance is basically 3 times longer than that one. So the ratio is about 3. On the other hand, we have then this distance divided by that, and this distance divided by that. So that ends up being something like 10 or something like that in this case. So our amplitude response at this frequency is somewhere around 10. Okay. Think of a point somewhere in between here. Then the distance to this pole and that one is about the same. Likewise here, almost the same. So basically, when we are down around, let's see, maybe in this point, we actually have the amplitude response around 1, roughly. Okay, when we are hitting this angle here, we have the 0 location exactly at the unit circle. So at that angle, we actually have local minimum goes to 0. Amplitude response goes to 0. And also here, which is a full angle of pi. So just sketching the amplitude amplitude response may look something like this, which is a low-pass filter. Okay. You don't need to do that graphically since we also have the MATLAB. But anyway, so just to show that this one actually is the distance. Okay. Wow. I kind of selected this nicely. So let's see, that's maybe about 100 degrees. Maybe 10 over 9 times pi over 2. 5 pi over 9. Okay, good. So that angle here is 5 pi over 9. Thus making a system for the MATLAB at the same time. So that's about half and half. Okay, that makes a good system. What about the other part, which was the phase response? Oh, excellent! That's why I'm called yliopettaja. Okay, so that's just mathematical truth. So this is the frequency response is something that you get when you put, instead of z, you have e to j omega. You evaluate that complex polynomial, rational polynomial in unit circle. E to j omega is actually a point in here at angle omega. And omega is directly proportional to our physical frequency. Okay, so if you take the absolute value of this one, you actually get that product of that point to each of those 0 locations divided by the same point distance to the pole locations. This is simply this part is simply a distance, physical distance in complex plane. You can actually do it even with the tape measure that one and calculate those values, and you get the ratio, something like that. Magic. No magic involved, actually. And after all, we have the MATLAB where we can do the calculations. Helps? Good. That's one way to avoid another explanation. You know, I was also a student at some point. All right. So then the phase response. Phase response is probably easier if I explain it in continuous time domain. So if we have a sine omega t going into any analog system, what we get out is the amplitude response at that that frequency times sine of omega t minus the phase shift. And the phase shift is actually the same as it's a function of omega. Okay. On digital domain, we can actually make perfectly linear phase shift systems. Only on digital domain. We can have linear phase shift systems. And linear phase shift means basically that this omega is actually that's theta. Theta of omega is directly proportional to the omega. which is quite kind of nice, since then the output is sine of omega t minus k times omega, means simply that we have sine of omega t minus k, meaning a constant time shift for the signal regardless of the omega. Okay, good property, especially if you are doing some, say, telecommunication system and have, say, omega 1, omega 2, and so on that are carrying the information. For example, dual tone multiple frequency kind of system. You want to have the package of those two tones to arrive at the same time to your system. Definitely. You don't want any non-linearity on your transmission media. Okay, so for that reason, the linear phase shift is very important property. Okay, so that actually also brings a also another response, which is the group delay. So phase response is 1, but then the group delay, remember that one from the analog electronics? Do you? That's a simple thing actually. It's the phase response first derivative over the frequency, and actually it shows the time delay versus the frequency. And this is exactly the same also for the sampled system. So 2 pi f n times ts would do exactly the same thing. It's just market, analog system. But anyways, the typically group delay for low pass filter would look something like this. If the this phase shift is nonlinear, then also that would be nonlinear. But anyways, that's the group delay as a function of omega. Good. And this is directly the time delay of different frequencies on the system. All right. Let me take a quick look on my responses in here to see did I already cover everything. Signal spectrum, okay. Spectrum, signal spectrum. Signal spectrum. One more thing, which is, well, that the frequency response is kind of the system spectrum, since you are simply taking the evaluating your impulse response, make it a transfer function, evaluate the transfer function at e to j omega. Actually, the signal spectrum is about the same. You evaluate the do the z transform of the signal and then evaluate that at e to j omega, which is exactly the same as you do a Fourier transform of your signal. Fourier, you have heard of Fourier transform, right? And in this case, actually, we do the discrete Fourier transformation. On 80s, it was very important that you could actually derive the fast Fourier transformation from discrete Fourier transformation, just to show how genius professors Cooley and Tukey was. Okay, but now we just actually use the fast Fourier transformation, meaning that basically we take the samples so that we have 2 to the power of some n samples. Then we can use the fast Fourier transformation. And the speed basically comes from the fact that when you're doing a ordinary discrete Fourier transform and start basically increasing n, then this is basically a parabolic equation. So that's n squared calculations must be done on discrete Fourier transformation. But when you start dividing that fast Fourier transformation or the discrete Fourier transformation on even and odd terms, see, I was learning in 80s. I know how it's done. Meaning that basically in the beginning it's a little bit slower, but because of the overhead of the dividing those in, but very rapidly actually it follows a n log n curve, and this is very small, something like only 4 or 5 data points. Then you can actually start using the fast Fourier transformation. Actually, if you're doing some linear filtering on pictures, then this is the only way you can still do it. On discrete Fourier transformation, a 2-dimensional Fourier transformation would take a very long time. Okay, so but anyways, so we are using the FFT to calculate the spectrum of signal, meaning that if we have a signal on time domain, after Fourier transformation, the discrete Fourier transformation, we have the amplitude spectrum and phase spectrum of the signal. For signals, usually only the amplitude spectrum is the important part. Okay, I'll just mark it like that. X omega. And the wrong marking. It's the Z transform on X evaluated at EJ omega. Okay, there we go. It's just a marking. Don't worry, we are not using that kind of markings in MATLAB. So amplitude response, amplitude spectrum of this signal actually would then look whatever it looks like. For example, this could be a DTMF. Dual tone multiple frequency kind of sampled data from that one, showing okay, we have these two signals there, and the frequency of those would tell you what is the key code for that DTMF signal. Okay, as I said, the phase response usually is not that informative, but if it is, then you need to also plot the phase response. phase spectrum. Okay. Uh, However, this is the fast Fourier transform is actually calculates only the spectrum for, well, 2 to n samples. And sometimes we actually are more interested about how the signal is changing by time, meaning what kind of spectral component the signal has by time, and then we are talking about spectrogram. Gram. Better. So that's actually a time series of spectra. So if we have a very long signal sample and you either want to know what happens in this signal, we start subsampling it. So this is our first subsample. Then we calculate the fast Fourier transformation to make the spectrum. I'll draw the spectrum a little bit differently now. So I actually do, this is the frequency axis in here, and this is the amplitude axis here, x, e, j, omega. Okay? And spectrum might actually look like that. Then we take another sample here. Okay, that would be the second. Do the same thing. And we actually have a little bit different frequency response, or the frequency components on that one, and so on. Then we take this time series and compress it to one picture. So spectrogram is actually this picture, where we have the time going from left to right, as usual, and then frequencies from 0 to Nyquist rate right here. And now the question where to put this spectrum information, it goes to this direction, meaning color coding of that, so that we have the sample 1, sample 2, and here we have the higher, okay, somewhere here we had a little bit higher components like that, fades out. We have, okay, let me change it like that, for example. In here we have the highest components here and something like that, and so on. So fundamentally what we will get is a kind of image which shows what kind of frequencies this sample has by time. Nice. So example, chirp, like, would go like this. Or ambulance. That wasn't ambulance. So this is peepa, peepa. Okay, ornithologists. You know the ornithologists, the people with the binoculars, not looking at anyone else's home at night, but on the daytime, on the fields, looking at the sky. The first ones are just weirdos. dangerous weirdos. Okay, so that actually is used also by ornithologists. They have this, if you have been reading some ornithologist book, get a real hobby first, and then basically there's some of this kind of spectrogram showing how this bird actually is singing. Okay, like and so on. And by the way, when you're doing the spectrogram, you can then also start doing some other kind of analysis like speech recognition. Speech recognition cannot be done in simply by time domain. You also have to have some sort of the spectral information there to basically you need to recognize different vocals and consonants, and that actually comes from the spectral image. Okay, so, well, the vocals usually are kind of that kind of image is longer, and then consonants, of course, they have wider spectrum, and basically they start with a lot of, like, this would be S. Sounds like noise. So the spectrogram also gives you some basic tools for voice recognition. On time base you cannot really do, since voice samples are also very random. If I try to speak exactly the same words time by time, they still do not correlate on time domain, because they are very still say some small changes, and even with a tiny change at the beginning will make the correlation evaporate. But on the spectral plane, you can start then correlating the spectral images, and that will be totally different thing. Good. All right. So let me take another look at the exercise. Yes, I have enough of theory here. The rest of that you already have read, right? Yeah. You already have read all of my notes there. Maybe watch the movies. How many of you have actually been watching my movies from the last year? No. Excellent. Good. So did you enjoy them? You don't have to enjoy that. That's educational material. It's not usually much fun, but anyways, that's the way we go here. Okay. Good. So let me go and continue with this. So today's exercise is about, okay, first part, you know already how to do that one. So determine the system parameters A and B from the following system. Then the, first values of the impulse response to figure out if this is a IIR or FIR system. So IIR is simply that it's infinite impulse response, nothing more. FIR is finite impulse response. So finite meaning it ends at some point and it's totally zero after that. All right. And the only way you can safely test it is to calculate the impulse response and check it. Okay, then the frequency response, that's very simple. And also, does the system have linear or nonlinear phase response? Good, that you can see. So linear meaning that you have the phase response looking like that on the passband. Linear. Then plot zeros and poles on Aga's diagram again. And there you can actually also make evaluation which frequency the system has highest attenuation. Okay, there might be some zeros on the unit circle then. Group delay, yes, we can actually calculate the group delay and insert a figure. So that will finally show you if this is linear or nonlinear phase response. For linear phase response systems, this is constant group delay. Okay, scale the system. Okay, wow, that's fun. Even more stuff. So scaling, we had the scaling previously also. And then we have the generating a sound sample just for fun. By the way, decibels. You really need to review the decibels. There's lots of errors on that part. And here we are again with the, well, now we have this, yes, signal to noise ratio again. So if there is a signal to noise ratio given, that's something, meaning this we know, which is the same as 10 times log of the power of signal divided by power on noise. Power of signal is the same as the variance of signal, which is a square of the deviation. So it's variance of signal or standard deviation of the signal on power of 2. Same thing for the noise. Power of noise is same as variance of the noise, which is the same as standard deviation of the noise squared. And on this scaling of the noise, you need the standard deviation of the noise. Meaning that, okay, I'll just simplify a little bit. So this is signal standard deviation squared, and for noise standard noise standard deviation squared. So I can take the square out. Then I have 20 times log of 10 of standard deviation of signal divided by standard deviation of noise. You know this. You can measure that. What you do not have yet is the standard deviation of the noise. Okay. So that's what you solve. And then when you generate the noise, you basically multiply the random numbers given by well, that generator, which is the rand n size of the signal. Okay. So that's the linear scaling factor for your this random number generator. Okay, now you know how to do it. Let's try it on this exercise again. Good. So back to the business. I think I opened already the MATLAB. Let's see. And then on the 8, okay, you will take the spectrum of the last 2048 points of this sample. Then plot the spectrogram also, and then filter. Ha! Sounds fun. Yeah, I should get real hobbies. Okay, good. So let's get the ball rolling. So this is the exercise 3 responses. First, should I take a picture of that? No, I'm not. Or why not? I'm not evil. First, let me create my system from the zero pole plot. So if I remember it correctly, I had 1 0 here, another here at angle of 5 pi over 9. Then I had these 3 poles. Okay, I need pole pair here at 0.5 and plus minus 0.5 plus minus 0.5 J. Okay, so this is just an example. You have this different system defined by a flow chart. All right, so we have the zeros at -1 and okay, this is actually column vector, zeros and poles on column vector. And then I have on unit circle J times then the angle and angles. Okay, J times 5 times pi divided by 9 times then J. Oh, 1 and -1. Okay, I think this will do it. Yeah. Okay, yeah, maybe. So I have J times 5 pi over 9 or 5 over 9 pi and plus and minus J because I have that one. Okay, good. Yeah, those are the 0 points. Then the poles are 0.5 is the one pole on the x-axis or the real axis, and then I have 0.5 times plus J times 0.5, and then I have 0.5 minus J times 0.5. Good. And I can check graphically that actually this one is what I wanted, Z and P. Yep, more or less the same as I expected. Sorry over the aspect ratio, it's the old projector squeezes this y-axis a bit. So that's what I wanted. And then I will calculate the system coefficients, A and B. A equals the polynomial which is defined by the roots, poles. There. Oh, that's nice. I could actually use, say, fixed point precision numbers even on a on the feedback term. How about B equals polynomial of from the 0 points? Ooh, that's not too nice, but it's kind of sort of, well, those are the ones what I got. Should I move that one a little bit? No, it doesn't move. Okay, so those are the system coefficients. Now I can actually start calculating different things like the, well, let me just for fun calculate again the C-plane to make sure that everything is okay. This should actually come up with exactly the same looking picture as the previous one. Yep, it does. So I have a system coefficients instead of just the zeros and poles. Next step, let's calculate a impulse response. And for impulse response, we need impulse. And for impulse, we need actually some indexes. For example, a vector that starts from negative side and then goes to the somewhere on the positive side. In this, actually, you need at least the order number plus 1 points. At least. So 10 is quite a good number here. And then we have the impulse is simply nn equals to 0. And I'll do the casting to double just for fun. MATLAB calculates just nicely without this one, but this makes sure that we have a double precision values instead of true false values on that vector. So this is the impulse function. And just for fun. Yes, I can. No, I can't. Just a moment. Yes, I can, but just a moment. I need to do it this way. So frustrating. Better. Can I draw it a little bit lower? There. Good. So stem plotting. Yep, that's an impulse. Good. Then the impulse response, meaning we have the system with its coefficients are B and A, and input is that delta. So our impulse response of the system is HH equals to filter BB AA DD. So this is the impulse response. And then we can stem that one like that. Ooh, cool. Okay, looks like that. Basically, our order number of the system is the highest order polynomial on our transfer function, meaning now we have the third order system. Well, you can also say from the number of zeros and poles is the highest of the number of zeros and poles. So here we have the third order system, meaning 3 poles or 3 zeros or both 3 and 3. Okay. So that's the order number here. If we have any non-zero values after that order number delay, then we have IIR system. So this is IIR system for sure. So we don't need to go to infinity and check if there is some values there. That'll be a little bit difficult too. So we just need to check if there are any non-zero values here, and that's it. This is IIR system. Okay, good. That's test checked. Next, let's calculate the frequency response. But for calculating frequency response, I would like to also have a really physical meaning for the frequency axis. So I'm just setting the sample rate, for example, 2 kilohertz. For example, a sampling system, a data logger of some sort. So this is sample rate, 2 kilo samples per second, KSPS. And then we can actually calculate the frequency response quite easily. Frects, and the system is BBAA. Okay, sorry about that one. The Frects actually gives funny help there. I'm used to this old-fashioned way of defining the system by vectors. That one, HS name and value, actually defines it by the newer kind of structured data, or closer to object data in MATLAB. But I'm an old geek, so I use this. And then frequency response BBAA, and then I have the number of points on the Fourier transform 1024, for example. Cannot. And then sample rate. That's the old way of using it, but I think you can actually take a document of that one. Signal display. Okay, there. Yeah, that's the old-fashioned kind of thing. So double-clicking and help on selection. No. Okay. See also. No. What did I actually click? Function browser. Yeah. Function browser. There are 3 different Frects. Oh, actually, 2 different Frects functions. One is on the digital signal processing toolbox, and another one is on signal processing toolbox. And I'm using the signal processing toolbox type. Okay, but anyways, like, there you go. That's nice. That's a frequency response of the system, and look at the scale here. Okay, that's about 70 dB. And difference between this and my whiteboard picture is that I didn't plot it here in logarithmic scale. And here you have the magnitude in dB. Then we also have the phase response decrease as a function of frequency. This is the passband, which is the most important part. And as we can see, this is definitely not a linear. So yeah, it deviates from the linear quite much, actually. All right, so let me zoom that a little bit. There we go. So, well, yeah, not a half bad filter, actually. You know, it wasn't quite 70 dB, but still about 40 dB attenuation on the stop band. Much better than what is that? Running average filter already. Just by, you know, putting some zeros and poles on the plot like that. Okay, good. One small detail here on the frequency response. Not a unity gain system. So we have a amplification also there. Most of the digital signal processing filters are made for unity gain, and that actually it's very simple to make. We just calculate the current maximum of that frequency response and divide parameters B with this value. So we can actually calculate or okay. So putting an output variable for our flex function actually gives you the frequency response calculated on those points. There. And then we can calculate what is the maximum gain, mg, equals maximum of absolute value of h. Absolute value is needed because, well, this is a complex frequency response what is returned. Not just the amplitude response, but it is a complex values actually. So that's the max gain of the system, and that's mg equals. Oh, okay, yeah, almost 20 times gain on the system. So what we can do is just simply divide the forward term parameters by that value. So we just basically add one more division on the system. And then, okay, frequency response again. Oh, wrong window. There we go. Then we have the frequency response. Oh, that's nice. We have the unity gain on the passband, and then about 40 dB attenuation on the stop band, and those couple of special points here. This frequency, that frequency are that and that here. Okay, so now we have also scaled the system to unity gain. We started from the zeros poles and then just find out the system coefficients, and then we could do the impulse response just by feeding the impulse function to the system, and then the frequency response. We could also try the step response actually. That would be a no-brainer actually. So just, okay, I will start it from here. No, I'm actually starting from, oops, ah, unit step response. To-do. Unit step response. How do I start it? Yes, I first need the step function. This is the step function. There. Okay, and then I can calculate, actually, when I calculate this one, that was the impulse response, just replace that one with S and that one with the U. That will be then the step response. And then stem. And that's the unit step response of this system. Unit step response of this system. Okay, good. So there you can then start figuring out what is the what is that? Those are called the rise time, fall time, settling time, that kind of things. Right. Good. Okay. Let me take a quick peek at the exercise sheet. Oh, group delay. Now I need some help. I don't remember what the group delay actually, what was the function for group delay. Group delay, GRP delay, that I think is the one. Yes, group delay BA. Ha. So again, we have this parameters B and A for the system, and this should actually, it probably also gives us that group delay. GRP delay, yes. I hope it actually gives me the plot. It probably does. Yes. So this is the group delay. And on the horizontal axis, there's a normalized frequency, x times pi times radians per sample. So it means that here's the 0, and here is the Nyquist rate, Fs over 2. This is directly group delay in samples. We can also feed in the sample rate to get seconds and the seconds and let's see. And hertz. So now it's a group delay. Oh, it's still on samples. Haha, that's great. I would actually put there the seconds. Okay, that's about 1.25 milliseconds here. So it's a 2.5 sample delay on the beginning, and then it rises here and then goes down here. Which also, this also shows that this is not a linear phase response. I saw it already on that phase response, so there was some diversion from the linear response, but this actually for linear phase response systems, you would get a constant delay, constant group delay. All right. Good. Another peek at that one. Yeah, that's the unit gain assessment. That's done. Ooh, wow. Then we'll generate again some noise. Calculate the spectrum of the last that point. Okay. Let me do some noise, but voice and noise. So some spectrum analysis. So signal spectrum analysis. And for that one, first I will take, for example, wait a minute, I have that sampling rate of 200 samples, 2000 samples per second. That's fine. I don't need any voice, or do I? Okay, maybe I'll just do a voice sample then. They're 44.1, so that's a audio signal sampling rate for good quality. Good. Then for a signal, test signal, I will make a chirp. So my signal, wait a minute. I need to find out the chirp. Help on chirp. Hey, that's nice. Ha! T, 10 second long, F0, 400 hertz. Anything else? Okay. Well, I'll just use that one. Not the examples here. So T sampling time vector 0 to and then the time step of 1 over fs to, for example, 2 seconds. Sampling time vector. Sampling time vector. Good. And then the signal itself would be S equals chirp. Time vector T. We start from 500 hertz, and then on T1, meaning the end time, that would be 2 seconds, we would have 2 kilohertz. So that's a 500 to 2000 hertz in 2 seconds. So something like that. Let's hear that one. Oh, that was pretty close to what I had.